So we're still working through a long problem from last time. We started out with a structure. We solved the structure, so we got all the external loads on every member. And then from there, we're going to calculate the internal loads, and from there, we're going to calculate the stresses at a point. So from last time, that's like a reunion today. So we have this member with an angle of 45 degrees from the horizontal. There is a force vector at this end of 11,470, 12,940. Then there's the distributed load of the weight. These are newtons. I'm just going to put that in to be clear about what's what. The distributed load, that's 1471.5 newtons per meter. And then we have another force vector here at the end of negative 11,471. Oh no, it's not an equilibrium. I think that's a round off error. You know, there's a 470 over on this side, 471 on this side.
I forced this one to be 471.
Okay, yeah. And then negative 10,000 here. Okay, that's what we got from the structures problem. Now we have to do the internal loads. So what we want to do is go from a coordinate system like this to a coordinate system with the x-axis pointed along the long axis of the beam, like this. So what's the angle theta that we have to come up with the rotation matrix for? Yeah, it should just be positive 45 because we're rotating counterclockwise to get from here to here. So theta is equal to positive 45. And that means that the rotation matrix is equal to, well, what axis are we rotating about? Z-axis, yep. So we have cosine of 45, sine of 45, 0, and then negative sine of 45, positive cosine of 45, 0, and then 0, 0, 1. And you get a value of 0.7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, and then 0, 0, 1. And if you look at the columns of this matrix, what you should have is this should give you so the columns here should give you the axes of the original coordinate system expressed in the new one. So in this new coordinate system, what are the signs going to be of the old x-axis? It's going to be a positive x component, a negative y component, right? We're talking about a vector like this, right? So it's going to be a positive x component, a negative y component, and that's what we got. And the second column should be a positive x component, positive y component, and that's what we get. And then the third component is the z-axis. Well, one thing that's worth noticing, telling yourself, remembering, is that no matter, like, whatever axis you rotate about, that axis doesn't change due to the rotation, right? It sort of makes sense if you think about it. So if you're rotating about the z-axis, that the z-axis in the old and the new has to be the same. So you always get 0, 0, 1 day. And so what we're really doing is coming up with yes.
If the one is indicated like a unit vector on the z direction.
Yes. Yep, that's right. So if you, these are all unit vectors. You know, if you take the magnitude of this vector, you get 1, this one you get 1. And the whatever axis you're rotating around is always going to show up as 0, 0, 1 because that doesn't change, you know. If you think of it as like, so if you, so say I rotate about my thumb, you know, rotate about the thumb, your thumb still keeps pointing in the same direction, and so that one's always unchanged. All right, so what we're doing is we're trying to re-express this in a coordinate system like this. And that's the same thing as lying it flat with a coordinate system like this. Those are the same. We don't care how, like, we only care about the math, the relationship between the coordinate system and the vectors. So we can draw it however we want as long as the orientation between the coordinate system and the beam is the same. Has anyone done those in multiplications and have it with them? Okay. Yes? You have it with you too? That would be great. So for the left vector?
Negative 1039.
Okay.
44.
1039? Okay. And what are the units? Yep.
17,260.
Okay.
3.
Okay.
And the one on the right is negative 10,000 or 1,040.
Okay.
0.14.
No equilibrium again. 0.14?
Yep.
Okay.
And negative 15,182.1.
15,182.1, and that's newtons. Okay, and then the distributed load?
Is 1040.5 newtons per meter.
And this is as a vector?
Yeah.
Okay, so 1030.5. What?
1040.
Oh. 1040.5 newtons per, and negative 1040. All right, I'm going to redraw this and break this vector, this distributed load vector up into a horizontal distributed load and a vertical distributed load because we're going to have to treat those differently. So we have the force vector of minus 10, let's just call all these 1040, and the y component is 17,260. Over here we have the vector of minus 1040, minus 15,182. Then the horizontal distributed load is pointing in the positive x direction, 1040 newtons per meter. And the vertical distributed load is pointing down with a magnitude of 1040 newtons per meter. Any questions about that? So now we're ready to do the cuts and calculate the internal loads. How many important points are there? 2, just at the end points. So we're only going to have one cut. That cut has to be valid over the whole length. So x is anywhere from 0 to 2. on the left, we have the force vector of negative 1040, positive 17,260. On the right, we have tension, shear force, and bending moment. And then we have a horizontal force. What's the magnitude of this horizontal force to the right? 7? 7 pi, I mean? No. Yeah, 1040x, because this is a distributed load. So this has to be 1040x. You could approximate it as 7 pi. Depends how good an approximation you need. And then the vertical force going down is 1040x.
Actually, I think my numbers were flipped over.
Oh. Oh.
My vectors. So the one on the left was just they're both positive to flip the numbers.
For which ones?
17, 260, and 1040.
Oh, they're both positive.
Yeah. They should be flipped over. And next to a negative sign. Right next to it.
Oh, okay. So your thinking is that they should both be positive, or?
They're both positive, and the 17, 260 is on top.
Oh, I see. Okay.
And the other one, they're both negative in the middle.
Okay.
And then the one on
That
the
makes
right-
sense, actually. Yeah, right.
And the one on the right, they flip it, and it's 1040.
Okay.
Or the 1040 is positive.
But other than that, it's right.
Yeah. Other than every number.
Yeah. Okay, so I guess let's start changing that. Okay, so this should be, maybe we should just multiply that out. Or you feel pretty confident about that?
It is approximated by 7 pi.
I know. So positive 17,260.
I just did it on my calculator, so.
Okay.
all these ones are right.
Okay, and then positive 1040.
Yes.
And then these should both be negative 1040. And then this one should be flipped.
Yep. Flip and 1040 is positive.
Okay. 182. Okay, so negative 15, 182, and this should be positive 1040. Okay, and that changes this direction for the distributed load. So that horizontal distributed load is pointing to the left. Okay, so 17,260, positive 1040. And now these distributed loads are right. And if I would have thought about it, we could have picked that up from eyeballing it for the distributed load, because
As far as like.
you can see that, this is just a weight force, that distributed load. So of course that's pointing towards the third quadrant of a coordinate system oriented, like that black coordinate system, Okay, one more. And on the right side, this is negative 15, 182, positive 1040. And the last change, oh no, two more changes. So this should be going this way. 1040x, this is 1040x. And this should be changed to 17,260, and then 1040. So Newton's second law says 17,260, and then y component of 1040 plus negative 1040x, negative 1040y, another negative 1040x, sorry, plus t negative v is equal to zeros. And so t is equal to positive 1040x minus 17,260. And v is equal to negative 1040x plus 1040. And then the rotational equation. Any moments produced by these forces on the left? Doing moments about the left endpoint? No. How about the distributed loads? Yeah, that's right. The vertical one produces a moment. And what's its moment arm? X over 2, exactly. And that's going to cause a clockwise rotation. So we're going to have a negative moment of 1040x times x over 2. And then we're going to have plus m minus vx is equal to 0. And so negative 520 x squared plus m minus vx is equal to 0. And so m is equal to 520x squared plus vx, which is minus 1040x squared plus 1040x. And so you get minus 520x squared plus 1040x. So now the checks. When x is equal to 0, should we have, so are there point forces when x is equal to 0? There are point forces, so both of these should be non-zero, and they are. At the right side, there are point forces, so both of these should be non-zero when x is equal to 2, and they are. And point couples, not at either end. So this should be non-zero. This should be 0 at x equals 0 and at x equals 2. When x is equal to 0, it's 0. When x is equal to 2, this is twice as big as that one, so it's equal to 0. So those all make sense. And what about the derivative? Okay, so yeah, dm dx is equal to v, so that works out. And we're trying to remember, the original problem says we want to calculate stresses at the midpoint, so when x is equal to 1. So t, when x is equal to 1, is equal to, can someone punch that in? $7,220. Negative 7,220. Negative 16,220. And then the shear force and the bending moment. And the units on the tension? Newtons, shear force? Newtons, and then moment? Newton meters, yep. Okay. So now we have those internal loads that we want, and we need to calculate the stresses due to, so the total stress at whatever point we want, and we're going to look at two different ones. We're going to look at it first here and second here. And we're going to do that by calculating the total stress as equal to the stress due to tension plus the stress due to shear force plus the stress due to the bending moment. Okay, so this is part A, this is part B. For part A, how do we calculate the stress due to the tension? Yeah, that's right. So we have a compression at that point of negative 16,220. Divide that by the area, which is 0.0010. Am I missing a 0? 0.5. No, that's right. And so you get a value of negative 1.62 times 10 to the 7, I believe, pascals. So the stress tensor due to tension is equal to minus 1.62 times 10 to the 7, zeros everywhere else, so now let's calculate the stress at the neutral axis due to the shear force. What type of stress comes from the shear force? Yeah, shear stress, and what are the components? Makes sense. XY, yep. So so now due to the shear force, we have the XY stress equal to VQ over IB. So we need to calculate Q and I. Oh, was the shear 0? Oh, that makes it easier. And then do the bending moment. What type of stress comes from a bending moment? Normal. And in this case, so to calculate that, we would have to calculate I. But at the neutral axis, remember the definition of the neutral axis is that you don't have any stress or strain due to bending. And so the XX stress due to bending is 0 because we're at the neutral axis. And so the total stress tensor at the point A is equal to negative 1.62 times 10 to the 7 and zeros everywhere else. And then for part B, So now we're going to do this calculation for the top of the cross section. Yep.
Okay, so would you explain more about how the bending moment will be dealt with?
Yeah. If you remember when we just first started talking about bending moment, that was when we first heard about the neutral axis. And the idea was that when something bends,
Yeah, when you go far away from the neutral axis.
yeah, right. When something, so if something's bending like this, what's happening is these elements are in tension, these elements are in compression. And so somewhere in between those two things, you have elements that are exactly the same length that they were before the deformation. And that's the definition of the neutral axis. So we are going to have to deal with bending when we do this line for part B. But at the neutral axis, you never have to worry about bending. Okay. So what's going to change up here at this point, or at this line for part B? Is the stress due to tension going to change? In a way, but in another more accurate way, the tension stress is not going to change at that point. So the shear and bending moments are the only ones where those stresses change, depending on where you go in the cross section. Okay, so we have a stress due to tension that's equal to whatever that was, negative 1.62 times 10 to the 7th. Zeros everywhere else. Okay, so now due to shear force, well, we had 0 shear force, so again, that's going to be 0. Remember that Txy due to shear is always 0 at the extremes, right? So it's always 0 at the top and bottom of the cross section. Why is that? So in that VQ over IB calculation, what goes to 0 at the top and bottom? V doesn't have anything to do with the cross section. That just depends on X, right? So that's 0 for us in this case, but that's not always 0. What about Q? Think about what that Q, how you calculate Q.
YC will be there.
That's right. YC, no, the area will be 0, right? Because remember for that V, for that Q, what you're doing is you're calculating the area above a line and then multiplying it. So if you're all the way at the top, there's no area above that line. And so Q has to be equal to 0 at the top or the bottom. So Txy is equal to 0. What about bending? Is that going to be 0 at the top? No, we have to deal with that one. Okay, so we know that it's going to be a compressive or tensile stress, and it's equal to negative my over I. So let's calculate that I. So I is equal to the cross section's base times height to the third over 12. The base for this cross section was 0.02. The height was 0.05. And so we have 0.02 times 0.05 cubed divided by 12.
2.08 times 10 to the minus 7.
Okay. And what's the y value going to be?
0.25.
Yeah, right, 0.025. Our neutral axis is right at the center, so it's half of the height of the thing. So y is equal to positive 0.025. And for this calculation, are we going to trust the sign that comes from these values, or do we have to think physically about what's happening? We can just trust it, yeah. You can remember that partly, I guess, because there's a negative here. Like, why would I bother to put a negative in front of it if you couldn't trust that sign, you know? So stress XX is equal to the bending moment, what was it, 520? What?
That 2.08 would be negative, right? We can trust the sign, but
That's just for I. That's not for the, this is just a calculation of I. So here's where the negative is going to come in. So negative 520 times positive 0.025 divided by 2.08 times 10 to the minus 7. And what do you get for that?
Negative 6.25 times 10 to the 7.
Negative 6.25 times 10 to the minus, no, 10 to the positive 7. What are the units? I like how you looked at your calculator. This is, it is newtons per meter squared, and that's pascals. And so, so the stress tensor due to bending is equal to negative 6.25 times 10 to the 7. Zeros everywhere else. Or was the, no, that's positive. The bending moment was positive, right? Okay. Okay. All right, so the final answer is that the stress tensor is equal to, or the XX component of the stress is negative 1.62 times 10 to the 7th. That's the one from tension. Plus negative 6.25 times 10 to the 7. So negative 7.87 times 10 to the 7. And so the final stress tensor is equal to negative 7.87 times 10 to the 7th, and zeros everywhere else. Any questions about that? So yeah, on the test, you'll probably have to do a problem of that type, you know, go from some kind of simple structure, or at least go from a beam that's leaning against something or at some funny angle, and go all the way to calculating those stresses. And how would you calculate? I guess we were going to calculate the strains too, weren't we? So to calculate the strains, you're just going to take, yeah, so the Voigt form of this stress is negative 7.87 times 10 to the 7th, and then 0, 0. And then the next one, yeah, but not that 0, the other 0, remember? Because of the funny order. So 0, 0, 0. And so the Voigt strain is equal to the compliance matrix times the Voigt stress. And based on what you get in the Voigt strain, you could you know, draw like a cartoon of what's happening to that member, you know, whether, like if you had, if you had shear strains, the signs would tell you which direction it's leaning, you know. If you have negative normal strains, you know that it's becoming contracted. If you have positive normal strains, it's what's going to, by the way, look at this one. Just from knowing physically what this means and what's going to happen because of this, what are going to be the signs of the values of the strain? Yep, that's right. So you're going to have, and I know that's sort of cheating. And how are you going to get the positives in the Y and Z normal strains? What Poisson's effect, yep. So that's, what that's saying is that we're going to have compression in the X direction, and there's going to be a bulging out in the other two, along the other two axes, because you're pressing down in the one direction. Okay. The next topic is, okay, so think about this for a second. Okay, so think about a beam, and the coordinate system is like this. There's X, there's Y, and there's Z. And what can you do to this? Like, how can you deform this beam? Well, you could elongate or compress along any of these three axes. So that's three possible loading types, right? And then you could also have bending moments about any of these three axes, okay? And if you think about it that way, we have talked about how to deal with every type of loading pattern you could apply to this member, except one. Okay, so if you think about compression and tension along these axis directions, we've talked about how to do this, right? Or stretching it. And we've talked about how to do these, although you have to worry about a little bit about the loading, you know, think about St. Venant's principle there, like you have a very short member. But if you wanted to do those calculations, you'd use the same equations as compression and tension there, and the same with the z-axis. And now, as far as bending, we know how to deal with bending about the z-axis, turning this up like a smile or down like a frown. We know how to deal with bending moments about the y-axis. Are you picturing this? This is supposed to be like a journey through space and time. It's definitely a journey through time. So we do those calculations the same way, right? I mean, it's just flipped over. But think about a pair of couples about the x-axis, okay? That's a different thing. We haven't dealt with that yet. That's taking one, doing that, and like twisting this thing, okay? So that's the last kind of loading that we have to deal with to be able to do any sort of simple loading pattern on any beam. And so that's called torsion. And you can represent that as a couple pointing one direction on one side and a couple pointing the other direction on the other side. This double arrow refers to a couple, and so that's saying on this side, you're applying a couple that follows the right-hand rule this way, and over here, you're applying a couple that follows the right-hand rule that way. And we have one mathematical preliminary that we have to go through before we can deal with that. So torsion will require one new, I guess I'll call it a mathematical skill. And this is expressing a stress tensor in a rotated coordinate system. This is going to be important throughout the rest of this class. So this is going to come up several more times. So notice that this is just sort of the tensor version of expressing a vector in a new coordinate system. So in some way you'd expect it to be the same, and they are really similar. So remember, well, let me, so in other words, we'll be talking about something, or I guess as an example, what we're talking about is going from a stress cube like this where there's some loading pattern, you know, 2.05 times 10 to the 7 or whatever. And calculate what the stress state would be in a coordinate system like this, where x is that way, y is that way, and z is that way. So what would the stresses be here? We know that for a vector, the same, what?
Wouldn't it be the same between the coordinate system with it?
Well, no. So the idea is that this stress cube, the stress cube represents a coordinate system. So like when we draw that stress cube, that's a way of sort of picturing whatever coordinate system we have, you know. I know what you're saying, but imagine that, so this member is still being loaded the same way.
So those arrows are going straight up the side of this thing. So is that what you're saying?
You would think so, but it's more complicated than that. That's what it would be. That's what it would be if this was just a vector. But a tensor is more than a vector. A tensor has information about faces and also information about directions, okay? If it only had information about magnitude and direction, it would be exactly like you're saying. So for a vector, yeah.
Is this like a screw something is changing the direction?
Like
Screwdriver, something when it moves.
that's what the torsion is, yeah. That's what torsion is. This is just a mathematical thing that we're going to use in torsion, and you'll see why as we go on. But so for a vector, we know that v in the new coordinate system is just equal to the rotation matrix Q times v in the old coordinate system, right? For a tensor, the stress tensor in the new coordinate system is equal to the matrix Q times the stress tensor in the old coordinate system, and then right multiplied by the transpose of the rotation matrix. And you can think of it this way. One of those two Q's rotates the cube, and one of those two Q's rotates the vector on each face. On each face of the cube. Okay. In my calculator, I have something entered in where all I have to enter is, you know, I have a program where I'll enter in 45 degrees about the y-axis or something, you know, and then enter the stress tensor, and it'll automatically adjust to the new coordinate system. I'm pretty sure that there's code like that listed on D2L, and so I'd recommend programming that in because you're going to have to do this type of rotation pretty often. Okay. Any questions? Okay, that's it.